An unusual object is moving so fast it could escape the Milky Way. Scientists aren't certain what it is. An object spotted with help of citizen scientists was moving so fast through the Milky Way that it could escape the gravity of the galaxy and reach intergalactic space, new research has found. Likely a faint red star, the object zoomed along at a speed of about 1.3 million miles per hour, 600 kilometers per second. In comparison, the Sun orbits around the Milky Way at a rate of 450,000 miles per hour to 100 kilometers per second. If confirmed, the object would be the first known hypervelocity very low-mass star, according to a team of astronomers and citizen scientists whose study has been accepted for publication in the Astrophysical Journal Letters. There are many more low-mass stars than high-mass stars because star formation favors objects of lower mass and stars with more mass have shorter lifespans, said study co-author Roman Gerasimov, a postdoctoral research fellow in the Department of Physics and Astronomy at the University of Notre Dame. But low-mass stars are harder to detect because they are cooler and less luminous. Hypervelocity stars, first theorized to exist in 1988 and discovered in 2005, are already extremely rare, which makes this new discovery particularly exciting, he said. Volunteers participating in a project called Backyard Worlds, Planet 9 first detected the star, named CWIS EJ124909.08 plus 360-2116.0, or J1249 plus 36 for short. Researchers involved with the project seek evidence of undiscovered objects or a large hypothetical world, called Planet 9, in the backyard of the solar system beyond Neptune. Backyard Worlds participants look for patterns and anomalies within images and data collected by NASA's Wide Field Infrared Survey Explorer mission, which mapped the sky in infrared light from 2009 to 2011. The space agency reassigned the mission as the Near-Earth Object Wide Field Infrared Survey Explorer in 2013 to monitor near-Earth asteroids and comets. Before retiring it completely on August 8, J1249 plus 36 jumped out to citizen scientists combing through the data a few years ago because the star was moving at about 0.1% the speed of light, according to the study authors. "I can't describe the level of excitement," said study co-author Martin Kabatnik, a citizen scientist from Nuremberg, Germany, in a statement. "When I first saw how fast it was moving, I was convinced it must have been reported already. Follow-up observations from multiple telescopes zeroed in on the object and helped confirm the discovery. This is where the source became very interesting, as its speed and trajectory showed that it was moving fast enough to potentially escape the Milky Way," said lead study author Adam Bergesser, professor of astronomy and astrophysics at the University of California, San Diego, in a statement, solving a cosmic mystery. The star's low mass initially made it difficult to classify, leading astronomers to question whether it was a low-mass star or a brown dwarf, a celestial object that isn't quite a star or a planet. Brown dwarfs are more massive than planets, but not quite as massive as stars, and citizen scientists working on the Backyard Worlds project have discovered more than 4,000 of them. But none of those brown dwarfs were speeding along on a trajectory that would carry them out of the galaxy like runaway hypervelocity stars observed by astronomers in the last 2 decades. Astronomers observed J1249 plus 36 using ground-based telescopes, including the W.M. Keck Observatory on Mauna Kea in Hawaii, and the University of Hawaii Institute for Astronomy's Pan-STARRS telescope located on Maui's Haleakaloha volcano. Data from the Keck Observatory's near-infrared echolette spectrograph suggested the star was an L subdwarf, or a star with a much lower mass and cooler temperature than the Sun. Cool subdwarfs are the oldest stars in the galaxy. The telescope data reflected that the potential star had a lower concentration of metals, such as iron, than other stars or brown dwarfs. By combining the data from multiple telescopes, astronomers determined the star's position and velocity in space, allowing them to predict that it will exit the Milky Way at some point. But questions remain about the true nature of the object. "I calculated the mass of this object to be approximately 8% of the mass of the Sun by comparing its observed properties to computer simulations of stellar evolution," Gerasimov said. "This places this object right on the lower boundary of allowed stellar masses, and it is in fact possible that the mass of the object is slightly below that boundary, which would imply that the object is not a star, but a brown dwarf instead, uncovering more details about the object could help astronomers determine whether it represents a broader population of high-velocity, low-mass objects that have undergone extreme accelerations, according to the study authors. Understanding its exact nature could also help them determine when it will leave the galaxy. Previously, astronomers have spotted the supermassive black hole at the center of the Milky Way giving a swift kick to a star, which will leave the galaxy for good in about 100 million years, a swift stellar kick. The researchers believe there are two possible scenarios that have placed J1249 plus 36 on its swift path. The study team said it's likely the star was a companion to a white dwarf star, which is the remaining core of a dead star that has expelled the gases that serve as its nuclear fuel. In these stellar pairings, if the two stars are close together, the white dwarf will siphon mass away from its companion and have an outburst called a nova. And when the white dwarf accumulates too much mass, it will collapse and explode in a supernova. In this kind of supernova, the white dwarf is completely destroyed, so its companion is released and flies off at whatever orbital speed it was originally moving, plus a little bit of a kick from the supernova explosion as well, Bergesser said. Our calculations show this scenario works. However, the white dwarf isn't there anymore, and the remnants of the explosion, which likely happened several million years ago, have already dissipated, so we don't have definitive proof that this is its origin. Another possibility is that J1249 plus 36 existed in a globular cluster, or a spherically shaped, closely bound grouping of stars. Astronomers predict that black holes with different masses exist at the center of such clusters. The black holes can form binary pairs that can catapult any stars that draw too near. When a star encounters a black hole binary, the complex dynamics of this three-body interaction can toss that star right out of the globular cluster, said study co-author Kyle Creamer, incoming assistant professor in University of California, San Diego's Department of Astronomy and Astrophysics, in a statement. Creamer carried out simulations and discovered that three-body interactions can knock a low-mass subdwarf star from a cluster and put it on a trajectory that is similar to that of J1249 plus 36. It demonstrates a proof of concept, but we don't actually know what globular cluster this star is from, Creamer said. Gerasimov is most intrigued by the idea that the object was ejected from a globular cluster because such clusters include stars that are older than 13 billion years. The chemical composition and the distribution of stellar masses in globular clusters capture the earliest steps in our galaxy's formation and evolution, he said. Yet, virtually everything we know about globular clusters comes from studies of their higher mass members, because low-mass stars and brown dwarfs are just too difficult to observe. The James Webb Space Telescope recently allowed astronomers to identify the first brown dwarfs in a globular cluster, which have a similar mass to the object. But there are too few examples, thus far, to nail down a broader understanding. However, the existence of this hypervelocity star, if it is indeed a former member of a globular cluster, opens a new way to study low-mass cluster members by looking for those that got ejected and are traveling at high speeds through the solar neighborhood, Gerasimov said. Since we were able to find one example, there are likely many more to be discovered in the future. Tracing the path that J1249 plus 36 has taken so far in reverse could lead to a crowded part of the night sky where undiscovered clusters are waiting to be found, the researchers said. Now, the scientists are hoping to learn more clues from the star's elemental composition, which could help explain how it ended up on a trajectory that soars away from the Milky Way when white dwarfs explode. They create heavy elements that could exist around J1249 plus 36. Similarly, stars in globular clusters throughout the Milky Way have distinct patterns of elements that act as a calling card for their origins. We're essentially looking for a chemical fingerprint that would pinpoint what system this star is from, Gerasimov said.